The question in questioned documents very often refers to the origin of a document. What created this document? What tool created this document? So I may wonder whether PDF LaTeX was used to create a PDF document. The tool may leave all sorts of marks on the document, and those are known as toolmarks, and hence toolmark analysis here in a digital sense. In general, I hope to be able to say that if I find a PDF file as an example, that it was created by PDF LaTeX, or that it was created by the photocopier that can output PDF files, or it was created by Microsoft Word that can also output PDF files. So I want to be able to say this is the generic tool that was used to create it. I'm talking about a class of tools. There are millions of instances of PDF LaTeX, and I'm talking about the whole bunch of them. Perhaps I can narrow it down to a specific version or set of versions, but even then I am talking about a lot of possible creators. Those are class characteristics that will hopefully be exhibited in the documents created by those tools. Individual characteristics are characteristics that are shown by only a single instance of a tool. So this tool that I have on this computer may leave some mark on it, on whatever I create with it, that tells me that it was created on this machine. However, that is obviously much harder to find in general, and the video will hence focus mostly on class-based characteristics. One of the fields of forensic science where we do see class-based and individual-based identification as very important is ballistics. So let's start with a quick detour via ballistics to get to toolmark characteristics of digital documents. One of the basic tasks in ballistics is to associate a round with the gun that fired that round. One of the easiest ways to do that is to look at the marks that are left on that round, on that bullet. And they are known as striations or striation marks. And those are basically scratches that are made when that bullet goes through the rifling pattern in the barrel as it exits the gun. The question is whether we can similarly associate a file type with the product that created that file type. Basic idea is when a product writes a file, there may be certain options, certain decisions that it may make. And those decisions include what compression level to use, what commands to use if multiple commands can achieve the same thing, and so on. And what we are hoping to do is to examine a file and then see the marks that are left, and from that trace it back to the tool that created it. I think it's Fred Cohen who first talked about these marks as tool marks, and in Fred Cohen's book he also uses the notion of attribution. So the file is attributed to the tool that created it, rather than to the individual that created it. When looking at files, we can distinguish on a superficial level amongst three types of files. Some files will be text files. Think about HTML files that by definition consist of text data. Some files will be a combination of text and binary data, and I am specifically interested in those files where we have a lot of text. In some binary files you may have a word here and a word there. That's not what I'm interested in right now. So I'm going to call my category, my second category, text-rich files. And that's the sort of thing that we saw in PDF files in the previous video. There was a lot of text in it that one could read, and then there was also a lot of binary data involved. And then the third category, in addition to the text-based files, the text-rich files, we have the pure binary files that should be interpreted from a binary format. The odd string of text that they may contain may be valuable, but the structure of the file is really on a binary level. So in this video, I'm going to focus mostly on text-rich files, PDF files, but some of the ideas will also apply to pure text files, and some of the ideas will also apply to binary files. The approach that I'm going to follow is one where I'm going to explore different files, files of the same type, but files that were created by different tools, and then look for differences that occur. Arguably, I could have also done this by looking at the specification of the file type and then see where the designers have an option to create something different, where they have freedom, and then search for those. But I think it's more interesting to at the very least start our search for differences by looking at differences that occur in the real world. Now note that we already in the previous video, in video number 2, looked at a macro dissection of the file. In that macro dissection of a file, we saw that the PDF file that we used consisted of a tree, and the way in which the tree was structured differed from one PDF creator to another PDF creator. Now this will be true for many file types. If you think about compressed file archives, the sequence in which they compress files, the way in which they decide which algorithms to use for compression, and so on, are all examples of such issues that I will call macro issues for the time being. So the macro issues that we considered in the PDF file were the type of nodes that were generated in the tree, and then also, very, very important, the sequence in which those nodes were unpacked in the PDF file. Note that the video that follows is intended to be a do-along video. I go through quite a couple of exercises where I manipulate a file, and just watching the video is bound to be rather boring. This video is intended to be stopped, where you can try the thing that I've done and then go on with the video to the next step. You probably won't have access to the same PDF files that I'm using in this video, but it's easy enough to find your own PDF files and then work along. To illustrate these concepts in a practical context, let's look at the Hello World file that we created last time. Recall that this was created with PDF LaTeX, and opening it up, you do see the textual elements that we spoke about. You also see the binary aspects. In fact, if you were to scroll through this, you'd probably see more binary aspects than textual aspects. But the point that is important for the time being is that we do have a lot of textual elements that we can work with. Let's look at the other file that we created during the previous exercise, and that's the version of the voucher that we wrote out as a PDF file with Microsoft Word. If I open that up, again you can see there's a lot of text that I can read. Similarly, if I would scroll down, there's a lot of binary information in there, but yet again I want to look at the textual information. So what we see here is that we have a type catalog pages. How to interpret that is not really important right now, but we are, for ease of reference, going to refer to each of these elements as a command, and we have a type catalog pages. And the important thing to note is that these run on without any spacing. There we have spaces. Whether we really need that space is an interesting question, but clearly we had a 2 and a 0, then that would have become a 20. So that space is necessary at the least. It almost begins to seem as if in this particular line there are no unnecessary spaces. Also note how this type catalog pages runs on and talks about metadata, it talks about viewer preferences and so on. This is all one long line that continues right up to that point. Lot of information packed into a single line. Let's go back to the Hello World example that we looked at, and I want to find the catalog pages, in other words, the same element that we've just looked at. And here you see type, space, catalog, and then there's a new line, and then pages, and then the necessary spaces. That shouldn't be 50, that should be 50. That's why that space is necessary. As a reminder, as we've said, this was created by Mictech. So, hypothesis that begins to form here is that Mictech may be using quite a lot of spaces. We need to do more testing before we can confirm it as a fact, but in this file at the very least, if we go right to the top of the file, it seems that in addition to these horizontal spaces, there's also a lot of vertical spacing, new lines that go on to next lines below that. Just scrolling through this, we see the type page contents, and we can see that that stretches out over a couple of lines with at least one horizontal space in there. Again, there is something that seems to be using quite a couple of new lines, a lot of horizontal spacing, and then we get to some binary information going via that, which takes a while, unfortunately. We again get to a set of commands, and there's a space, and there's a space, all horizontal spaces that we did not really see in the Word version thus far. In fact, if I go to the creator, then here we can see that even after commands such as producer, creator, and creation date, we have spaces between the command and what follows in brackets. So, general feeling is that this layout uses a lot of vertical and horizontal spacing, and it almost gives us the feeling at this point that the only reason why we don't have a new line in there is because trapped false probably means that trapped, whatever it may mean, happens to be false, and we could probably make that true. So there is some semantic relationship between those two things that are placed next to one another. Returning to the word voucher example, then we see the opposite. Very few spaces except where they make a real difference. There's a line that runs on quite extensively, as we've noted previously. Going to the next object, again we see very few spaces between the commands, and again there is a line that runs on extensively, contains a bunch of information. In the same way, if we go down via the binary information, we again see type, font, subtype, true type, and so forth, all into one long space. So what this suggests is that we can distinguish between two files created by either LaTeX or Microsoft Word by looking at the spacing of the text elements, and we will immediately be able to recognize it as being created by the one or the other. Just as an aside, we also wanted to look at the creator or the producer of this, and what we see in the producer is indeed that there's no space left after the word producer. Similarly, there's no space after the modification date. There's a little space before the creation date, but the creation date itself, again, no space. There is this rather interesting thing. If we look at the producer, then we do read Microsoft Word in there, but we see null characters between every character in Microsoft Word. So there is yet another distinction between the two. In the PDF LaTeX, it was quite readable that PDF LaTeX created it. What we are claiming is that we can distinguish between files produced by these two tools, PDF LaTeX and Microsoft Word, at least in the current versions that we are talking about. Wider testing, as I said, would be necessary to make those general claims. What we can do in a case where we have a binary file is the following, and I'm going to switch to a smaller font just to make things more easy to fit onto a screen. And I'm going to say, let's do a hex dump of all PDFs.zip. For our first attempt, I'm just going to send it through the less filter, and you can see that there is some information that can be read. Hello world.pdf appears there, but by far this seems to be binary data, and again, very little that I can do with that by pure visual inspection. So to analyze this file for differences between this zip creator and another zip creator, I will have to use a different strategy. So we've looked at two text-rich files here. The one was Hello World, the other one was the word voucher. During the previous exercise, we also worked with a utilities.pdf. This is the utilities PDF that was received from the municipality. So it's not one that was modified by QPDF or PDFTK. And if I open this one up, then I can yet again see that this one seems to be rather shy to use spaces. Again, there's a long run on that we are getting there. If I go down again, I see a lot of binary information, but I also see things that look like XML, which is something that I did not see in the previous file. If we try and find the producer of this file, or the purported producer, then we can see that this is an Adobe Experience Manager Forms output, and clearly some Adobe tool that was used to create this. There is a creator tool provided. We therefore are looking at files that were created by three different tools: PDF LaTeX, lots of spacing, and then for Adobe, this Adobe tool, rather shy to use spacing, and for the Microsoft Word tool, also rather shy to use spacing. In this case, we saw some XML. One of the questions we have to ask is whether the XML is also present in the Word file. We can begin to look at other distinctions here. We are seeing line feed characters, but did we see that in the Word tool? So let's quickly go back and edit our Word voucher. And there are indeed line feeds, so that does not enable us to distinguish between these two tools. What we need to do is to put these two files that seem to be shy of using spaces next to one another and find some way to distinguish between them. I don't want to use the metadata, because the metadata is the very first thing someone will modify. The challenge that I'm facing is the fact that I want to use text editing tools to operate on these mixed files that contain both binary and textual data. Now, why this is a problem is that the text tools are often designed to manipulate text, characters. And with the introduction of, in particular, Unicode and things like UTF-8 encoding, a character can occupy more than one byte. And when the text manipulation tool encounters a byte sequence that it considers, that it deems to be one character, then it will treat it as one character. However, it also means that some characters are illegal or invalid. For example, if you encounter a continuation byte in a text string without a preceding byte to start the sequence, then that is deemed to be an error, and the text editing tools will often ignore that. Given that we have binary data in the middle that is not textual at all, we may easily have a sequence of characters or a sequence of bytes that, when interpreted as characters, are invalid. The type of manipulation that I want to perform is something like using the set tool to remove all the streams, because the streams are the places in the PDF files where I encounter the binary data. One or two other places as well, but I don't worry about that for the time being. So I generally want to use something like a set tool, give it an expression where I say take every begin stream and end stream. Now, begin stream is just the word stream. Take everything between those two brackets and remove it. I also know that set is going to take the first stream and the last end stream and remove everything because it's greedy. That's not my concern right now. The fact is that I cannot use set in this manner because set will be confused by the binary data. To illustrate that, consider the example where I say take a file and remove everything from it, every single character. And then when we look at the file afterwards, it turns out that the file is not empty. It still contains data. That is entirely counterintuitive. So I need to find a workaround to process files in this manner. The workaround will be where I turn every file into a hexadecimal stream, and then I search for whatever I need to search for using hexadecimal notation. One of my options is to say XXD and then use the P option to omit the spaces and also the ASCII representation of printable characters in the right-hand column. And if I were to apply this to hello world.pdf, then you can see this is just a sequence of bytes, all in hexadecimal. In this long sequence of hexadecimal bytes, I want to be able to locate things like stream and end stream. And one way of locating them is to determine what they look like in hexadecimal. So if I try end stream and I pipe that through to XXD with the P option, then I get the hexadecimal equivalent. And I can now easily select it. Note that the 0A at the end is a line feed. It's not part of what I gave it, so the M ends with a 6D, and I can copy that. Similarly, if I just want to look at the value stream, and I get a stream, it should be a substring of what I received up there. Again, it has a 0A included, and again I copy that and I store those two away so that I can search for them in what I'm going to do next. Remember that the binary data can be anything, so these markers, these delimiters that I'm searching for, like stream and end stream, may accidentally occur in the middle of the binary data. So ideally, before I use them as markers, I should search the file that I want to manipulate to make sure that they only occur at the places where I expect them. For example, in a file in which I have two streams, if I look at the file initially before any decoding or any conversion, I would expect the word end stream to only occur 2 times in a file with 2 streams. On the other hand, the word stream will occur 4 times, twice in the end stream word and twice on their own. And if there's any other use of stream in it, then I am in trouble and I need to work around. Let's take our file that we've just now looked at in hexadecimal. The option does exist for this file because this is a pure text file, that I can edit that with a plain old text editor, or that I can use commands like set. However, if I want to search for something like stream in here, it is possible that stream may exist on a line break and so on. So what I'm going to do is take this hello world, dump it for me as a hexadecimal file, but I'm also going to use the translate command tr, and I'm going to say delete for me, and what it should delete for me are the new line characters. So this turns this entire dump, hex dump, into one line of hexadecimal codes. And in order to play with it a little bit more in a moment or two, I can just send it to a file. Let's call it x.hex as a temporary storage space. If I were to open x.hex in a text editor, then it is again one line long and it's all hexadecimal. What I've done a moment or two ago is I've sent all of this to a file called x.hex. But what I can furthermore do is I can now invoke set, and I can say substitute, and I can paste in the hexadecimal value of end stream, and I can now replace it with a special token that will enable me to find it. However, the special token that I'm going to put in there is simply a new line. The reason why I want to put in a new line is because set works on a line scale, and it's going to yet again find the very first one or the very last one for me. And when I want to replace the streams, it's better if every stream ends at a line end. So because I've just used a new line, I can put this in quotation marks to ensure that I don't cause any problems. And I'm going to close my substitution bracket, and I'm going to say that I want to do this on a global scale, and yet again I'm going to redirect the output to the file x.hex. So looking at this file x.hex, we can see that it now consists of 3 lines, so it suggests that we had 3 streams in there, and we can explore that further in a moment or two. What I'm going to do now is to eliminate the streams entirely from the file. So let's take this file that we stored a moment or two ago, and rather than sending it immediately out to hex, I am going to invoke the set command again. Note that I could have added this as an extension to the previous set command, just another set of parameters, but I'm going to do it separately to keep my parts separate, and then we can later on think about efficiency and that sort of thing. So what I want to do here is I want to substitute. Now I need to find the value that represents stream. So I'm going to search for that, and then I'm going to say from that point onwards, any characters right up to the end of the line should be replaced with nothing. So I am effectively taking out this stream. Again, this will by definition be a stream that ends at the end of the line, so I don't need a G there. I can simply say that that's the replacement that I want to make, and I'm going to send it yet again to x.hex. So at this point, I should have in x.hex all the streams removed, and I should be able to revert the hexadecimal that is left to something that is textual. So I'm going to cat that x.hex file and then pipe it to xxd, and I want to reverse the process at the moment, but my hexadecimal is no longer in a standard format, so I have to add the P option to say this is just a stream of bytes that's coming in, and I am then going to send this out to y.pdf. Obviously not a PDF file anymore, but let's do that anyway. If I now open up y.pdf, then you can see that we do have text and all the streams. For example, there we had something that was Flate encoded, and it is gone. This is pure text, and it becomes very, very easy to print this out. 116 lines, it's about 2 pages of A4 paper. Print this out and put two of these next to one another and do the comparison. In order to reiterate what I've just done, my problem was that I had a mixed file. It contained text data and binary data. Now, if I were to manipulate that file with the text tool, the binary data could confuse the text tool. In particular, if the text tool were to think that it is Unicode that it's seeing, or if the text tool were to encounter binary data that would be a UTF-8 representation of Unicode data. So for that reason, I wanted to remove the binary data. In particular, the binary data that I wanted to remove were those streams that were delimited by the word stream and end stream. So in order to do this without using a text tool, at least initially, I converted the entire file to a hexadecimal representation. I also converted the two markers, stream and end stream, to a hexadecimal representation. And now I was able to use a text tool to work on this hexadecimal file, because this hexadecimal file is a text file. And I was able to replace everything between the stream and the end stream marker with nothing. Delete it. And after all this was done, I converted the hex file back to its original representation, which now should consist only of characters, which is exactly what I got. Tiny caveat, I still had some binary data in line 2, but that is not the portion that was giving me problems. If I really want to delete line 2, it's easy enough to do. Now we are at a stage where we have collected, let's say, millions of PDF files that were created using different tools. We've removed the binary from them, and we have put them into categories according to tool, and we've looked at the differences between the various files. We think we know what those differences are. We know which differences occur in all files, which differences only occur in some files, and we are ready to begin to differentiate our files, other files, based on the tool that created them. How do we proceed? Well, one option is to generate or write a grammar for each and every file that we've encountered. That grammar can spell out exactly what may and may not occur in a given file. In fact, with open source, we can probably get the grammar from the source code itself. Once we have generated all these grammars, once we've produced all these grammars, we can build parsers, and then we can say that this parser will recognize files that were generated by tool A. Second parser will files that were generated by tool B, and so on. And we can validate this parser by running it on our various source files, make sure that it works, and we can source some additional files, some few million more, and perform these tests exhaustively. In some cases, we may have to differentiate between versions of a tool. This version generates files like this, that version generates files slightly differently. And then we can send a new file through all our parsers, and all our parsers will look at the file and say, yes, it could have been this one, or no, it was not this one. Slightly different approach would be to build a decision tree and look at the differences between the files, and then as we go deeper and deeper, we find more and more differences. And whenever we have a tool that generates a file that looks like that of another tool, we again find something that differentiates them. However, we don't have thousands or millions of files in this course. We also don't have the time to work through those millions of files. So I'm going to use a significantly simplified approach here. And you will realize that this approach does not scale. We will have to go to something much bigger to make it work at all, but to keep it small initially, we're only going to use the 3 files that we've used thus far in the video that were produced by the 3 tools that we mentioned earlier on. And we will see how to deal with those cases and then talk about generalizing it somewhat. So let us explore that file from which we've ripped up all the binary stuff. Remember, this one was created by Mictag. We realized that it has a lot of spaces in, spaces between what we called command, for lack of a better term, and also vertical spacing in terms of putting things below one another, where some of the other examples did not do that. So the challenge with this is to find things that look promising to distinguish this from other files. We see a length, but we recall that we've seen lengths in other files as well, and we concluded in that case that there was probably a necessary space after length. The type that we see here, type page, is useful, but I'm going to suggest that type in general, /type space / is something that we will see all over the place in this file. We will return to that in a moment or two. It's not clear that context and resources and so on are going to be useful. We're pretty sure parent will not be useful because they'll probably all have parent objects in them. The question whether the fonts in the other files look the same in terms of a font specification, for that I'll have to do a comparison. I don't want to go to that file right now. I rather just want to scroll through this. And again, we see various lengths. Can't remember whether the others had a length 1 and a length 2 and a length 3. So yet again, it's something for us to go and explore. I'm pretty sure the others had a filter Flate decode, and they didn't have a space there. There we again see type, promising thing that I'm hoping we'll encounter often. And then going through this, there are a couple of other things, again, a type that we see there, a couple of other things that I see that may be useful. I'm not sure though, because I need to compare it to the others. I, as noted before, want to stay away from this metadata as far as possible, but I do recall that we saw a space here which we didn't see in the other cases. But metadata may be replaced by something totally different. So that makes me want to avoid that. I'll go down to the end. What I've not taken into account in this quick scroll through is the vertical spacing. So what I am suggesting here is that we may use a pattern, something like the following. Let's say if I want to know whether PDF Flate created it, to search for type with a space and another slash, because that's something that I've seen quite often in this PDF file that I've just worked through. I want to test this on the original file that was the Hello World that we used initially, and I want to see whether type occurs there. And it tells me that it does match. Then I want to try this on the Word voucher. Remember, that's the one that was created by Microsoft Word, and there's absolutely no feedback, so that does not match. So this is an indication that it differs from what was produced by PDF later. The final file that I want to compare is that utilities bill that was created by the Adobe tool, and again there's no match. So here I have found an overly simplistic example of a way, given that I only have 3 files and 3 generators, and that string enables me to identify files of the first type. The question then is, if the type does not match, what does the type look like? So I want to go and look at something like the file created by Word, and I specifically want to see what the type command looks like, and there we find it all. And what we see is that type is preceded by angled brackets in this version. So is this perhaps a way to identify files that were created by Word? Let's clear this, and then I am going to say grep, and I'm going to look for those angled brackets, and then type, and don't know whether it was clear, but the type was always immediately followed by a slash. And I want to look for that in, first of all, our Hello World program, PDF LaTeX, and it doesn't find it. Look for that in the Word produced file, so hopefully it finds it there, because that's where I saw it, and it does find it. And then the question is whether this is able to distinguish between something produced by utilities. So again, rather weak examples that I'm using here, but they begin to illustrate the notion that I am talking about. Question to continue that is, what does type look like? So the command type in the utilities file, and this time I don't want to treat it as a binary file, I want to treat it as an ASCII file, so that I can see what type looks like. And what we see here is that apparently type also immediately has a slash following it in general, but it seems from this very small example that we always have an alphabetic letter, or at least in many cases have an alphabetic letter before it. So what I'm proposing is that we are going to use this command grep, and what I want to do is to look for an alphabetic character, and after the alphabetic character I want to see type. And let's try this on the utilities bill, because that's the one where we saw it. So this should be able to tell us that that Adobe tool was used to create it, and it does indeed match. Now trying this on our Hello World created by PDF later, it does not match. And trying this on our Word created voucher, it does not match. So what I have created here are three tools, three tests that will take a file and tell me whether that file was produced by a specific generator. It's almost like testing for the coronavirus. I have a specific test, and if it comes out positive, then I know that that virus is present. Here I know, if that test comes out positive, that the specific generator was used. However, I've worked from the overly simplistic assumption that there are only these three generators, and there are obviously thousands, if not more, of generators. So clear experiment that I need to do is to find some additional PDFs and run my tests on them, and they are bound to fail. So I need to get something that is more robust, that will not fail as easily as this one fails. There's something slightly concerning about what we've seen just now as well. In that file y.pdf, the one from which we cleared the streams, there wasn't a lot left that would enable us to recognize the creator. Yes, we can perhaps look for things that are never used, commands that are never used by PDF later, that are commonly used by other tools. So we also should look at what we don't see. And I stressed that we had vertical spacing that we didn't see in our other examples. But it seems as if something more is necessary to get a robust match. Rather than just waving hands, it makes sense to look at how we can extract the binary strings and uncompress them. In this case, I'm not going to go through the entire step in a developmental way. I'm rather going to give you an answer, and then you can work with that and do your own experiments. So what I start out with is, as I've done in the past, am converting this hello world.pdf to hexadecimal digits, and then I am stripping away the new lines, so the entire file becomes one long string of hexadecimal digits. At this point, I want to search for the streams and the end streams and use those to delineate the streams so that I can extract them. So the first command that I'm using here is that particular one, and that one simply says search for end stream. That's the hexadecimal of end stream, and whatever you find after that. So whenever it finds an end stream followed by anything, it's going to delete all of that. Given the greedy nature of set, it will find the first end stream in the file and then stretch that to the end of the file, because that's going to give it the longest possible match. So if I wanted to find the second end stream, I'll need to convert this, I'll need to play with this. However, there's something that I learned through doing this, and that is the fact that the end stream command always, in this particular file, in Hello World, starts with a new line. and the new line caused problems when I decompressed it. So what I'm actually searching for is that 0A, it's new line, end stream. I do have other files here where you have a character return line feed before every end stream, and that will need a slightly different approach. So the 0A in particular is just the new line, so I'm stripping away the new line and the end stream, and this will then, at this stage, leave me with the entire hexadecimal file up to just before where the first end stream in the file occurs. Then in the next step, and yes, I could have combined these two set commands in one, but let's keep them separate for the time being. I am saying search for all streams. So wherever you find the word stream. But before that, I am telling it to look for any characters, and then whenever it finds stream, it should delete that. So everything is deleted. In this case, I found that stream in my original file had a new line at the end, and again that new line confused the uncompress algorithm, so I had to also get rid of the new line that followed the stream word, the stream tag in the PDF file. In this particular case, because I've stripped out everything from the first end stream there, this will find the first stream. That's the only stream that should be left in there. In general, if I am stripping out other parts, I may have to rethink whether I want to search for the first or the second stream and so on. I'm going to leave that as an exercise for you. So at this stage, I have deleted everything that followed the end stream, including the end stream itself. I've deleted everything that preceded the stream. And at this point, I only have the hexadecimal representation of the stream contents. So what I can do at this stage is I can convert it back to its original binary representation. And then what do I do with that binary representation? Well, I want to uncompress it. And here I have a simple little uncompress utility that will deal with that Flate compression, and I can either use a specific command or I can just use the -d, which will tell it that it should decompress. So I've extracted the entire binary string in hexadecimal, converted it back to binary, and now I'm going to uncompress it, and with a bit of luck we will have some readable text when I push enter. And you can indeed see there that we have readable text. There's a little bit of a marker before it and a marker after it, but I have uncompressed it. One of the lessons that I learned from doing this for the second stream was the fact that the second stream was not textual data that was compressed, but it was already binary data that was compressed. So what I got as an output here was binary, and that makes sense. If you are, for example, encoding a font, then that font encoding may be binary, and you should not expect text. Here we had the hello world. This is the content of the file, which is obviously textual. But for many other things, we should expect binary data, and we should deal with them as appropriate. There are some partial contents that I want to extract from this. The one thing that seems useful is to extract the text. So I'm just putting the text that we've just seen in x.txt. So I've got that stored away. And then the other thing that I want is I want the file before it is uncompressed. So the xxd minus reverse the hexadecimal representation, and this is no longer in a standard format, but that will give me the binary output, and that is a Flate encoded file. So I'm just going to put that in f.dat. These are just two names. So f.dat is my compressed file, and x.txt is my uncompressed file. The reason why I've done this is I've been saying all along that we can look at compression levels, and we may be able to identify the file based on the compression level. Remember that at this stage we have the binary data stream in f.dat, and the text that we've extracted from that is in x.txt. That's what it looks like. The question that arises is whether we can compress the text and see whether we can recreate the compressed representation. That is a fairly dangerous thing to do, because we do not at this stage know whether the compression algorithm is unique. In other words, whether whenever you run compression on a string, you will get the same encoding. In fact, in any compression algorithm, the important aspect is that when you uncompress it, you get back what you started out with. There's no need to always get the same. So the fact is that we have already used the PigZ tool. Now that's just an easy access to the zlib. And what we can do with it is to say that we want to use the zlib representation, not the gzip representation. And furthermore, we can in fact begin to say how much it should be compressed. So the options are that we say it should be compressed by 0. In other words, do not compress it at all. It will generally leave it a bit longer than what we started out with, but that's fine. And then we can, as input, provide x.txt, and then as output, just for the sake of comparison, I'm going to output this to f0.dat. The question then is whether the f0.dat looks the same as the f.dat that we stored as a reference format. One fairly easy way to do that is to just ask whether there's a difference between f0.dat and f.dat, and the answer is that they do differ. We can go up from 0, no compression, right up to 9, which takes in principle the longest time, but hopefully gives you the best possible compression. PigZ also includes an 11, which can give you slightly better compression, but at significantly longer time. But it's there, so we may want to look at it as well. However, note that there is nothing that says that the original compressed string that we got from this PDF was indeed created by zlib. It could have been generated or created by any other compression algorithm that just followed the rules of deflate compression. So we can continue with this process, and we can in the end go up to a stage where we say, I want to compress up to level 9, and I want to store that in 9. And again, I can do a comparison just like I've done just now, and in this case compare F9 to our reference sample. And in this case it matches. So somewhere between 0 and 9 we do find a match. Now, I've actually already created all of these comparison files, and we can easily check F8, and there's a difference. which means it looks as if PDF LaTeX uses level 9 compression. Just for what it's worth, if we compare 11, then we also get no difference. So we don't quite know whether the compression of 9 or 11 was used. However, there's a danger in what we are doing at the moment. This suggests to us that if zlib was indeed used in the implementation, then we are fairly sure that we can identify the appropriate compression level as probably a 9, but possibly an 11 for PDF LaTeX. However, if we look a little bit further and we look at all our files created for this purpose, then we can see that apart from F0, they were all 96 bytes long. There's a 96, there's a 96, there's a 96. In other words, none of these yielded any better solution than the other, except, as we said, F0 that added header information and then no compression, and therefore increased the length. The fact that we do get something identical suggests something positive. However, the question that we have to contend with is whether the deflate compression is consistent, whether it will always do the same thing, whether it will always yield the same result. And the simple answer is no. If you read the specification, then you will see, amongst others, there are portions in the specification where it tells you that certain bits have to be skipped up to a byte boundary. So whatever is written in those bits make no difference at all. And this presents us with a challenge when we do the type of comparison that we are doing right now. In order to try this on at least one other example, let's try it on the word voucher. Remember, this was written by Microsoft Word, and again we are searching for end stream and we are searching for stream. This works in exactly the way we did this previously. However, when one looks at word voucher, one sees that it uses a carriage return line feed combination at the end of every line, not simply a new line. Therefore, where I previously had a new line, I had to this time also get rid of the carriage return. So I had to add another byte in at the beginning of that string. That's simply because every new line is indicated by that old DOS convention. Similarly, in the case of the stream, where previously I could simply say line feed, I this time had to say carriage return line feed to make this work. So this means we have to check every file to see what convention it uses, and it is not always the case that they use exactly the same convention throughout the file. So running this, we get our x.txt, which is the textual portion of that particular file. So let's just look at it. And one of the things where it differs significantly from the previous example is that it is much longer. So now we can yet again try and compress it. So it's again the PICZ, and we want it in zlib notation. And we can, for example, say I want level 9, in other words, highly compressed, but it may take longer. And I want to get this from x.text, and I'm going to put this in f9.dat. And then I can do my comparison as I've done it before in the case of Hello World, and I can say let's compare our standard, in other words the one that we extracted from the file, to what we got from this compressor. And it tells us that there are differences. So we can go and try 11. In fact, I did, and there is nothing that matches. So let's try a slightly different approach here to reach some level of certainty about what's going on. If I tell it to list all the files for me, so there is F0, F11, F1, F2, and so on. Right at the bottom is our reference file that we started out with, and the length of that file is 1047 bytes. Now, if we go through this, then you can see that compression 0 led us to 4,600 bytes. That's very, very long. 11 made it much shorter than our reference sample. And then F1 was slightly shorter and so on. And 1047, we reach at about the F6 or F7 level. And if you go and compare those files that we get there, then they literally differ in about 4 bits from our reference sample. And as I've said, we don't expect a unique compression necessarily, not even if we know that zlib was being used, because there are some bits that are sometimes skipped. But we're not even sure whether zlib was used, and that may have chosen other values for the Huffman encoding, or other values, or even chosen an alternately different compression technique, given that there are essentially 3 compression techniques used in deflate encoding. So we may want to reach the conclusion here that Microsoft Word uses more or less a level 6 or level 7 compression compared to the level 9 compression that we saw in PDF LaTeX. However, before we reach that conclusion, we will have to test thousands of files, or where the source code is available, perhaps inspect the source code to know what's going on. Again, these levels are not standardized as part of the algorithm, so therefore we are getting these from the zlib implementation, which we don't even know has been used. So we should tread very, very carefully here, but hopefully this gives you a way where we can start to do comparisons and put it out there as a hypothesis, and then go and test the hypothesis on a very, very wide sample of files. This latter exercise leaves us with almost a recursive problem. Number one, can we determine which compression library was used? There are a couple of very well-known deflate compressors, and it may be possible to identify the compressor library, and once we've done that, we may speak about with more authority about products in which a compressor was used. The second question that also arose rather quickly was that in that decompressed example of the Word file, which was quite lengthy, we saw that there was also some structure, and perhaps that structure can also be analyzed, both its macroscopic aspects and its microscopic aspects, to help us to classify the PDF file in terms of the tool that generated it. In all of these cases, we need to vastly expand our experimentation before we can make any conclusive remarks. In the end, you hopefully reach the point where you begin to see things that we may look at and that we may use to determine the origin, at least in terms of a class of a PDF file. The fact that we have also worked with compression a little bit hopefully means that when we begin to talk about file formats where compression are used, and just think about PNG or gzip or JPEG, all of those use compression. And that may be the key to unlocking the origin of those files. However, that is definitely not the only key. There are many, many other aspects that one should also be able to look at to trace a file back to its origins. How certain can we be about the results? Well, that we will only know after extensive testing. It is, however, worth exploring other options beyond what we've just looked at, and that is what we will do in the next video.